I should really say the real mastermind behind this work is my graduate student, Jordan On, so you can wave and ask him any technical questions or any tough questions rather than asking me, okay? But before we get into the talk, I wanted to just say a couple of things about where I come from and what are the type of problems that really motivate our work. So I am a statistician by training, and I'm a professor of statistics at Penn State, but I'm like an old lady in the picture above. I've been working on privacy for actually quite some time right now, and particularly focusing on understanding privacy from a statistical perspective. And what that means is that I am really interested in problems of how do we enable sharing of data under, in this case, rigorous privacy guarantees to maintain data utility for statistical inference and prediction. I specifically highlight these two things because in machine learning, there's a greater focus on prediction. In statistics, we really try to do both inference and prediction, and I would say inference is even more so important. And just to be clear about what do I mean by inference versus prediction, so let's consider just a very simple example of a linear regression model, which I assume most of you are familiar with. And I'm interested in predicting somebody's income given a series of characteristics. In machine learning, I am interested in finding the best model that will give me the smallest error of prediction, particularly in forecasting the future data points. In statistics, like James was talking about yesterday, if I'm a social scientist, I'm interested in more than that. I'm actually interested in understanding the structure of the data generating mechanism. And actually, if I have those regression coefficients, which we typically call beta in a regression model, they mean something to me. They tell me specifically about how is the income changing as a function of somebody's age, or somebody's health status, or something to that extent. And those correlations is that I'm interested in estimating, and I typically want to say something about their properties and what they tell me about the underlying population of interest. And for that, we do hypothesis testing, confidence intervals. So that's what we are interested in also when we talk about statistical inference. And I'm only touching on a little tiny part here, but I wanted to make clear that the distinction between prediction and statistical inference. Because I think that makes doing all the developing differentially private mechanisms a bit more difficult in terms of both theory and implementation, okay? So I have a nice group of students who are working on various problems that are listed here. So clearly we're working on some rigorous privacy definitions and stuff that I'll talk about a little bit today. We have work on private work on social network data, genome-wide association studies, a lot of work on distributed databases, to some extent related to what we have heard over the last 2 days. We have some new work actually on functional data, differentially private functional data, which I'm pretty sure there's not much work on that. I'm not going to go into that at the moment. And we have a lot of work on what we in statistical disclosure limitation call synthetic data. Okay. Couple of people who are involved in this project, Michelle Pisner on the top. She's working a lot on some synthetic data methodology. Ann Johnson is doing more something with record leakage. Yuji is doing some work on distributed databases with health data in particular. Joshua Snow, who is here, you can talk to him about what he does, but he's actually on the job market. So if you're looking for a great person to join you, please talk to him. And Jordan, definitely speak with him, and he might be interested in some outside research experiences for the summer. Okay. And most importantly, I have postdoc positions available. One is a visiting assistant professor position, and the other one is, I would say, a regular postdoc position. These are in the statistics department, and we have collaborations with people at Penn State, like Dan Kiefer, also with a lot of people outside Penn State, Adam, to mention only few, but I didn't want to spend too much time on this. Okay. So let me get back to the problem that I want to give you an overview of today. So thinking about how we enable sharing of the data to enable statistical inferences in particular, one problem that we wanted to look at was how can we improve utility of differentially private information sharing for real value statistics T, income, age. We heard a lot of work on discrete data, sums, histograms, etc. Of course, we work on that as well, but we wanted to focus more on real value functions. We recasted that objective into a problem of how can we compare K-norm mechanisms to optimize statistical utility, okay? So what we do, we introduce what we call the adjacent output space. We connect that adjacent output space to the notion of sensitivity, which is, you will all agree, key to differential privacy. And we have definitely heard discussions yesterday and today about the importance of how we define sensitivity. We then have a theorem that actually formalizes how we can compare K-norm mechanisms and decide which perhaps is the best mechanism. And specifically, we can derive the optimal K-norm mechanism using this geometric space that we will define, S of t. And for more practical perspective, we actually extend the current results on objective perturbation and functional mechanism to arbitrary K-norm mechanisms and show that we can save about half a privacy budget if you understand the structure of the adjacent output space correctly. Okay? So in essence, this is the roadmap of the talk. Okay? So again, we're at this point, I think, all familiar with definition of differential privacy. I wanted to bring this slide up just to be clear about the definition that we are using, specifically the definition of what is the measure that we use for measuring the distance between the neighboring databases. Again, in relation to yesterday's discussion, so we are using the Hamming distance. So for us, n is fixed. Okay, so it's the same. So everything that we from here on talk about is under this particular definition. Okay. I also wanted to bring your attention to a particular interpretation of differential privacy that is due to Wasserman and Zhou's paper in JASA in 2010, which I think it's often ignored, but for statisticians, and I would say perhaps a lot of practitioners, it's a much nicer intuitive interpretation of understanding of differential privacy. And what it basically says is that a mechanism, a random function, satisfies epsilon differential privacy if you have a hypothesis test that says, is this record a person U or is it a person V? Okay, this is a well-defined statistical test in statistics. And when we say at level alpha, this is a type 1 error rate. Typically, in scientific literature, by default, is assumed to be 0.05, but it can be really any number. And that power is bounded. The power of this test is bounded by alpha e to the epsilon. And basically what it says, given that the values of epsilon we typically utilize, it says you have no power in figuring out if this is a person's U record or person's V record. Okay? And so if you explain this for anyone who has taken a basic statistical course and has done a simple hypothesis testing, they should understand what this interpretation of power means. So I wanted to bring this to your attention, especially as you're working with researchers and applied researchers. Let's say I think it may be a useful definition to use to communicate the understanding of differential privacy. Okay? So how can we achieve epsilon dp? And everything we're talking about here, we're specifically working with the strongest definition. So we're going to consider K-norm mechanisms proposed by Hart and Talwar. And we're going to define the sensitivity of our real value vector, T, in the following way. Okay? And we're going to use this sensitivity. Basically, we are going to release this real value vector by drawing random noise from some kind of exponential density. Okay? This is what exponential. Do we have actually a pointer somewhere here? Maybe this. Does this work? Yeah, OK. So from this exponential density, which clearly shows that the variance, right, or the noise here will be scaled to the sensitivity I compute, which is not different than using your Laplace mechanism. And Laplace mechanism is a special case of the K-norm mechanism. So this is a generalization of the Laplace mechanism. And the k-norm mechanisms can be considered special cases of the exponential mechanism, okay? So, so this norm here, as I'm pointing out, gives the Laplace mechanism. Other commonly used norms, or most commonly used norm besides L1 is L2 norm. And L infinity norm has been discussed, and most recently in a paper by, I'm going to mispronounce the last name, Steinman and Ullman? Steinke and Ullman. In 2017, they actually discuss only from a theoretical perspective using L infinity norm, okay? We will work with these norms as well through our more general setup of k-norm mechanisms. And we will point out that they're also probably popular because they're actually easy to implement in comparison to using any arbitrary norm. But everything that we talk about here holds for any arbitrary norm, okay? So it's a really, we hope, we believe, nice general result, okay? So commonly used norms can be any other norm. So I think the natural next question would be to ask, well, if the norm I use, if the sensitivity is related to the norm I use, and this impacts the amount of noise that I add, what is perhaps the best k-norm that I should use? And is there a way that I can actually compare these k-norms in a more formal way so that I can make an informal and theoretically supported decision which k-norm to use, okay? So to do that, we consider, as I said, the geometry of the output space, okay? That we define this adjacent output space of our real value vector t. And we show that the sensitivity is basically the upper bound on this geometry that we define. This will become more clear through a simple example. More specifically, the sensitivity is going to be the radius of the smallest norm ball containing this, what we call adjacent output space. So again, here U is just the difference in the outputs for the given two adjacent databases. Okay, so let's look at I think a simple example. Okay, so let's assume that we have a database X where our records take values between -1 and 1, and we're going to consider a simple a statistic that has two entries, the sum of the xi's and sum of the two xi squared. Okay, and what we do by defining this adjacent output space, we clearly go from considering 4 values to now only need to basically work with 2 parameters, u1 and u2. And here's the space. This is actually the geometry of that S of t space. Okay, so why? Oops. Okay. So why am I looking at this? Well, because when we need to draw the variance vector, the vector for the noise, sorry, v, we'll be drawing it somewhere from this space, depending how you further bound perhaps this space. I mean, ideally, you would really want to draw it directly from these two, I guess, from the wings of the butterfly. I don't know. This looks like a butterfly to you. Okay, so what we can do, we can now, because we define the sensitivity, right, as the upper bound here, so we can actually compute the exact L1 sensitivity. Okay, we can compute the exact L2 sensitivity, and we can compute the exact L infinity, right, using L infinity norm. So what I'm doing here, I'm showing you basically this, the diamond is your L1, the oval is the L2, and the square is your L infinity ball. And ultimately, what I will be doing here, if I'm using these sensitivities, I will be drawing the V, the noise vector, from this diamond, square, or a circle. Okay. So what often it's done in practice, however, because nobody really wants to do a lot of calculus, as Jordan pointed out, we do approximations. and they could be rough. So I'm not going to go through details of this, but you know, if I do a little bit of approximation work here, these are actually the upper bounds that I get, and those are the sensitivity values that I will use in my formula to define the variance for the exponential density that I'm using, okay? So now if I look at these approximate sensitivities, right, again, I have the diamond, the circle, and the square, but you should notice here that they're contained within each other, okay? So this should give you a little hint that there is maybe a nice way to do this comparison and to figure out what would be the best ball to draw the noise from, right? Because you want to use the minimal ball here to draw your noise from, to minimize the variance, okay? This is just comparison to the exact sensitivity, where that comparison is a little bit harder by simply looking to figure out by simply looking at the picture, right? Because they overlap, okay? So what we do actually, and I'm not going to go into details of this theorem because I believe I only have 10 minutes and I want to get to some examples. We provide a theorem where actually you can exactly compare any norm that you desire to sample, to use to define the sensitivity from. And we can actually tell you what is which will be the variance that will have the uniformly smallest variance, depending which norm you're using. So here, you know, I'm considering norm K and norm H, and I can tell you we can show you when V of K has uniformly smaller variance than V of H. And V is the noise vector that we're drawing given, you know, the K norm or the H norm. And if you can do this mathematically in a nice, provable way, I mean, this is, I think, a pretty nice result, okay? So, for example, applying that theorem, right, even if I don't draw this picture, but I rely on these approximate sensitivities that most of us do in practice, we conclude that in this particular case, L infinity norm has the smallest norm ball. So you should use the sensitivity L norm sensitivity and basically use alpha L norm, L infinity, and use the L infinity mechanism in this case rather than using L1 or L2 mechanism, because this will give you the smallest variance in your noise, thus leading to better utility and better inference down the road, okay? So, but you can do even better, right? And the better is actually looking at the convex hull. Okay, so our results basically show that the uniformly smaller variance than any other norm is the convex hull around this norm that we're considering. Again, I'm not going to go into details on this. But even though that's beautiful result, and in some cases it could be reasonable to compute, the problem of computing convex hulls is a general computational geometry problem, and it's not always easy, right? So perhaps there is getting the explicit description could be difficult at times, right? Okay. So on the other hand, if we again focus on L1, L2, and L infinity, they're all easy to implement in a way that I didn't talk about. There are nice ways to actually sample from these exponential densities, okay? And you can still use our theorem to compare them, again, to make an informed decision of what to use. So let's look at, I have about 5 minutes. So let's look at two specific examples that a lot of, I think, people work on, okay? One is a linear regression, and the functional mechanism is one of the popular mechanisms proposed for releasing linear regression in differentially private manner. Zheng et al. 2012. There are other mechanisms out there, some more recent, okay? So the setup is we're considering the observed axis, so these are predictors in a regression model to use the typical statistical language, and Y is our response. We certainly pre-process them, which is a common thing when we do differential privacy. And actually in statistics, it's not that uncommon sometimes to pre-process them, especially if you have issues we call linearity, in terms of like bounding them in between -1 and 1, okay? So the model is Y is the linear function of the betas. The betas are parameters of interest, okay? And this is something that, as I said earlier, social scientists and statisticians are actually interested in knowing the best estimate of the beta, typically the maximum likelihood estimate, and having some sense of the error of the estimation for this beta hat, okay? There are many different ways you can fit a linear regression model. In this particular case, we're going to rely on a vector of sufficient statistics. So here, our T is a vector of real value functions, sum of the xi's, 2xij squared. We're already seeing basically what that adjacent output space looks for these two functions together. And then you also have the product of x's and the product of x and the y. Okay? So basically, sufficient statistics says once I have these four quantities, I can estimate betas without any problem. Okay?
This epsilon is not the epsilon of differential privacy, but you want to say?
Oh, sorry. Yes, I should. Yes. Bad notation. So yes. So in statistics, the epsilon typically in the linear regression model refers to the errors in the model, and they're assumed to be normally IID, 0 sigma squared IID. So sigma squared is invariance. Thank you for pointing out. Yeah. So this is not a DP epsilon. This is a. We should have changed that notation. Okay. So we're going to sanitize this vector via using the k-norm mechanism, okay? And we're going to compute this estimates of beta, and we're going to compute the differentially private estimates of beta. And this is here the generalized inverse that we're using. And this is a well-known least squares formula for the linear regression estimates, okay? So here, the optimal k-norm mechanisms, right, which we can actually derive using our work, is non-trivial, but I should say Jordan worked it out, okay? And so here is going to show you some results on actual real data. So this is housing data from San Francisco Bay between 2003 and 2006. Of course, we do some pre-processing. There are 7 continuous predictors. And here we also have 5 indicator variables, so binary 0, 1. Even though I was talking everything in terms of saying we are working with real value functions, the work actually applies to discrete values and integer values as well, okay? So we have, ultimately, we deal, our sample size is about 200,000 data points. So it's still on the order of magnitude less than 1 million. And we run this model for each value of here, epsilon is the differentially, for epsilon for the privacy budget, okay? We do 1,000 replicates of this model. And then we compute here what we call the relative log likelihood, and we compute actually the median over these 1,000 replicates. So we fit one model, we define the estimates, we compute the log likelihood. We look at the difference between the differentially private estimate beta hat and the maximum likelihood, which you would have gotten without doing any differential privacy. We rescale that, renormalize that, okay, to get some nicer looking plots. And over these 1,000 replicates, we look at the median. You can look at many different things. Looking at this relative log likelihood is basically like looking at the mean square error. So for those interested in prediction, this gives you a pretty good plot. And what does it say? Here is the range of the epsilon values. So this is basically your privacy versus your utility or accuracy curve. Laplace is the lime green curve, Laplace mechanism, L1, okay? And L infinity and optimal are these blue and red, which pretty much overlap here, okay? And so what I would like to point 2 things out here. One is that if you use optimal or an L infinity mechanism in here, you basically, for the same accuracy level, you're saving half the privacy budget. Just by simply looking at the geometric structure of the adjacent output space, understanding where you're really drawing the noise from that you're adding to your functions of interest, okay? So that's, from our perspective, that's super important. And this gives us some sense of these betas and how they relate to what you have gotten without doing anything differentially private. So for us, this was a big plus. If we consider logistic regression and objective perturbation, again, which is another very common mechanism that has been proposed, here, the same space for the predictor values, the y is the response 0, 1. Now we measure the sensitivity of the gradient, okay? We're minimizing this log likelihood with some penalty terms, et cetera, not going into details. And now we want to compare these 3 mechanisms again. Here, coming out with the optimal mechanism is a bit more difficult. So this plot here, what we do, I guess we have 10,000 observations, right? So what I want to point out here before going into the plot is that these are now getting into more realistic sample sizes that a lot of social scientists will be looking at. So I was talking to Ashwin earlier, and I said, hey, for us, if I do a t statistic, asymptotics kick in with a real value mean, average, kick in at size, a simple size of 30 if I have some a normal distribution, right? So think about what we call finite ends in a way, although asymptotics should be kicking in here. Here, I just want to point out that now we're looking at the median L2 distance between the truth, because we know the truth, and the differentially private estimator. And again, we're showing that L1 is not the best. L2 is certainly not the best, but L infinity is the best mechanism, again, to use, okay, to get the best utility from our perspective. And actually, there was a paper that recently claimed that L1 is better to use than L2 in objective perturbation with logistic regression, and clearly that was wrong. Okay, so I love geometry. Jordan loves geometry, maybe. It's all about geometry. So often Laplace mechanism and L2 are used without considering the geometry of adjacent output space, and we believe it should be considered, okay, if you want to get better utility. We show the sensitivity is equivalent to the smallest norm ball containing this adjacent output space that we define. We actually have a theorem to formally compare k-norm mechanisms and decide which one you want to use. And there's unique best k-norm mechanism, actually, that you can derive. We can, especially for common approximations, it seems that in examples we looked at, L infinity is strictly better than L1 and L2, and even though it has not been used that much in practice, okay? And again, in our work that we looked at, we have some substantial improvements in performance from a utility perspective for linear and logistic regression. Okay? Thank you. Yes. Sure.
Yeah, so if I understood correctly, what you're doing is you're typically kind of constraining the space of possible databases to something like an L infinity ball, and then looking at what that ball becomes when you project through the statistic and look at differences in adjacent.
So we are constraining the output space. I mean, we look at we pre-process the data in this case because it's easier to compute these adjacent output spaces. Perhaps we should look at it, what happens if you don't pre-process it and work on the general domain. But the adjacent output space is on the output. So if I'm looking at the sum of the xi's, I'm looking to define that the convex hull and everything else with respect to the sum of the xi's and the sum of the xi squares or whatever other.
Right, but that,
yes.
the quantification there is for any databases drawn from
yes.
this L infinity ball. Is that right?
For any database is drawn. So what I'm drawing from the L infinity ball is the noise.
So no, but there's the x's, there's the databases
yes.
inside there. And you're quantifying over any adjacent databases where each database satisfies an L infinity?
No.
No.
The difference in the statistics.
Statistic. Difference in the statistic.
No, I understand that's what you're going to look at in the end.
No. This is what we're quantifying to decide on the noise. It's a difference in the tx, like
yeah, so I know but the question is, when you're defining the set,
yes.
you're taking the t of some database x.
Correct.
Right? And that database x is drawn from where?
The database x is a observed data that I have. It's not drawn from, I mean, it's a data that I have.
It's not a
so you're computing, so it's not a worst.
Oh, but I'm looking, yes, I am looking at the space of all possible data. Yes, I'm looking
so
at the space of all possible, yes,
okay. So,
yes.
Right, so you're not doing a data-dependent notion of this set. It's looking at all possible databases that satisfy something like an L infinity constraint.
Yes.
So my question then is,
sorry.
Have you, have you thought about, for the problems I work on, like with gradients, often the statistic is actually very simple. It's not going to be a very interesting geometric transformation of the underlying database, but the database itself may have a lot of structure. Like real-world databases may not fill that L infinity ball. They may have some other structure. So I'm wondering if anything you've done there will help where I believe that databases live in some other shape.
So there is something that we discussed a little bit in the preprint, and I think Jordan can probably say more about this, that where we say something about, what's the word I'm looking for? Help me out, near, yes.
You have to know the structure a priori. Like
Right.
it's not a correlation.
Right,
between
so
variables.
yeah, let's say I know it a priori, so I don't have to worry about the privacy cost.
Yeah, it might be possible you could then forward that structure
Yes.
into this.
Into the, yeah.
We have some discussion on a couple of simple examples where, like, if you just assume complete independence in the database versus, and then how that translates to the statistic, or actually think about independence of statistics, but there is some relation to the underlying data. So a couple of simple examples about that. Adam.
So because of time, why don't we take
You're
further
good, okay.
questions? So maybe I'll just take my liberty as chair, just make
Okay.
a comment. So
Yes.
this when you use L2 norm here
Yes.
and the K-norm mechanism, it's kind of easy, at least for me, to get confused and think it's the same as the Gaussian mechanism, which is something that one would naturally use.
Sure.
Like in the
Okay.
Analyze Gauss paper, you
Yes.
add Gaussian noise to the
Yeah.
variance covariance matrix.
Okay.
And this is not the same thing, and you're getting pure differential
Pure, yeah.
privacy, and the noise distribution is different. And
Yes.
Yeah.
Yes.
Yeah.
Yes. Yes. It's a stronger result because you're getting stronger privacy. Yes. I thank you for pointing it out. I guess we should make sure we point that out in a paper as well.
all right, thank you.
Thanks.